Hi, my name is Liran Alon, and today I'm going to present to you about improving KVM x86 nested virtualization. So who am I? I'm an architect on OCI, on Oracle Public Cloud infrastructure. There is such a thing. On the past 4 years, I work on virtualization, SDN, and cloud computing. But most of my experience is actually in the security area as a research and developer. And I'm an active KVM nVMX contributor, and also a very active Twitter user. So you can feel free to follow or direct message me at any time. So what I'm going to talk about. So even though the title says x86, I'm only going to talk about Intel CPUs. And it's really hard to talk about all the improvements that we have made to nVMX during the past year. So what I decided to do is to deep dive into one specific mechanism that I think had the most issues statistically, both in this year and in the previous year, which is event injection. And this mechanism was built over time by fixing edge cases and bugs. And there is no other public documentation besides the code, so I think this is a good opportunity to do that. And I believe that some of the lessons that we have learned during building this mechanism is also relevant to other architectures that just now add nested support, like Power 9. So after I will deep dive into this mechanism, what I will do is I will present only in very high level the past year work that's done on the nVMX. And I will highlight some pending open issues. And to finish, I will suggest some of my own personal ideas on what should maybe be the future direction of nVMX. So I will start with a very, very quick introduction to how nVMX works, for those not familiar with. So here we see a layer 0 hypervisor that runs a layer 1 guest. And it does so by creating a VMCS that I will name VMCS 01 to signify that this is the VMCS used by layer 0 to run the layer 1 guest. Now, because we're talking about the nested case, layer 1 also creates a VMCS that we will name by the same convention, VMCS 1.2. But when layer 1 actually tries to run the layer 2 guest, this will actually trap to the layer 0 hypervisor, which will need to emulate the correct behavior. And what the layer 0 will do is basically need to run the layer 2 guest on the behalf of layer 1. And the way that it will do that is that it will create a third VMCS called VMCS 02. And it will basically be the logical merge of the constraints written both in VMCS 01 and VMCS 1.2. And after layer 0 has created this VMCS, it will run directly the layer 2 guest on the behalf of layer 1. And at some point of time, this layer 2 guest will trap to the layer 0 hypervisor again. And now there are two options of what the layer 0 hypervisor can do. The first option is that this exit that just now happened from the layer 2 guest needs to actually be handled by the layer 1 hypervisor. So in this case, layer 0 will need to emulate an exit from layer 2 to layer 1 and resume the layer 1 guest. But otherwise, it will just behave as usual. It will just handle the exit on the layer 0 hypervisor. And after it will handle the exit, it will re-resume with the active VMCS, which is VMCS 02, and therefore run layer 2 again. So this is basically the high-level flow of how nVMX works. So after we understand that, we have the basic background to talk about the nVMX event injection mechanism. So when I'm talking about event injection, I'm talking about the mechanism that is responsible for injecting events. And events are interrupts, exceptions, NMIs, and SMIs. So in order to understand how this mechanism works for the nested case, we first need to understand how it works for the non-nested case. So here is a very simple example of a layer 1 guest that does a read MSR operation. And this operation is being trapped to the layer 0 hypervisor. Now, layer 0 sees that this read MSR specifically is attempting to read an unhandled MSR. And therefore, the hypervisor decides that it should queue a general protection exception. Now, the way that it will do that is that it will save a pending exception in a per virtual CPU software struct. And after that, it will request a special KVM request called KVM rec event. Now, this request, as usual, is evaluated on the next entry to the guest. And this KVM rec event is responsible for deciding what we should do with all the events that are queued on this per virtual CPU software struct. And in this case, it will see just that we have a queued pending exception, and it will just want to inject it. And the way that it will do that is that it will take this queued exception, write it to the active VMCS, and then just resume the guest, which will cause the CPU to inject the exception to the guest. So this basically sums up how it works for the non-nested case. Now, when we are trying to talk about the nested case, this gets only a little bit more complicated. So now the layer 2, the read MSR operation is being done from the layer 2 guest and not from the layer 1. And let's also assume that the read MSR trap does not need to be reflected to the layer 1 guest. So everything behaves the same. Layer 0 now emulates the read MSR. It also decides to queue a GP. But now when the KVM rec event handler runs before resuming the layer 2 guest, it also adds another special check. It checks if the virtual CPU is in guest mode, which means that we're currently running layer 2. And if we have any queued event that should cause an exit from layer 2 to layer 1. And in this case, instead of just writing the exception into the active VMCS, which is now VMCS 02, instead it will emulate an exit from layer 2 to layer 1. So this basically sums up the most simplest scenario for the nested event injection mechanism. But now let's start to complicate things with more possible scenarios. So the next thing that can happen on x86 is that when the CPU attempts to deliver an exception, the exception delivery itself can fail. And such an example is that when the CPU tries to deliver an exception, it needs to write the exception frame to the stack, but the stack of the guest can be unmapped on the EPTs of the host. So in this case, the CPU cannot really deliver the event. And what it will do instead is it will exit on EPT violation, but also it will record inside a special VMCS field called IDT vectoring info the event that the CPU has attempted to deliver, but could not because of the exit. So the way that KVM handles this, and again, we're talking about the non-nested case, is that on every exit from the guest to the host, KVM checks if this special VMCS field is valid. And if it is, it basically just takes the event that was recorded there by the CPU and queues it as an injected event in our virtual CPU software struct. And then we request the KVM rec event. So what will happen is basically that when the CPU exits during the attempt to deliver the event, KVM will requeue the event on the software struct. Then on the next entry, it will handle the exit. And on the next entry to the guest, this KVM rec event will see that we have a queued exception, and then basically just re-inject it to the guest. So this is the way that it works for the non-nested case. And now let's try to take also this scenario also to the nested case. So now we are talking about a scenario that the CPU attempts to deliver an event directly to the layer 2 guest. But this, again, the CPU has failed to do so because it encountered a condition that should result in an exit. So now this diverges into two possible scenarios. The first one is that the one responsible to handle this exit is actually the layer 1 guest and not the layer 0 hypervisor. And this means that the exit should be reflected to layer 1. But it should not just be reflected as usual. We should reflect it to layer 1 that he has got an exit during an attempt to deliver an event, exactly like the previous scenario. So this basically means that we also need to take the queued event that we have put on our software struct and put it on the VMCS 1.2 IDT vectoring info, because this is going to be the field that layer 1 will look at to understand if it got an event during an exit during the attempt to deliver an event. Now, the other scenario is that the exit that occurred during the attempt to deliver the event to layer 2 should actually be handled in the layer 0 hypervisor. So in this case, the layer 0 hypervisor needs to handle the exit. But after that, this event that we need to re-inject into the layer 2 guest must not be able to be intercepted by layer 1. And the reason for this is that once the queued event was written to the active VMCS, layer 1 should never be able to see if that this event was not actually delivered because layer 0 didn't prepare the environments right for the event to successfully be delivered. From layer 1 perspective, it already had its chance to intercept the event when it was first queued, and after that, it's injected from his perspective. Now, one may ask himself how exactly that in this case, the KVM rec event handler of layer 0 actually knew that layer 1 must not intercept the event, even though the virtual CPU is in guest mode, and we do have a queued event that should cause an exit from layer 2 to layer 1. So the answer for this is that we have a state attached to every queued event, whether it is in an appending state or in an injected state. So in the first example that I showed you with the read MSR, the queued event has entered with an appending state. But once the event was written at least once to the VMCS, then from this point onwards, the event is going to be with an injected state, even if we queued it after an exit during the attempt to deliver it, like in the previous example. So if I return back, you see that here we also queue the event in an injected state. And this is very important for nVMX code to have a clear separation between these states, because otherwise, basically, the KVM rec event handler cannot know if this event can be intercepted by layer 1 or not. And we had many issues of not separating this correctly for all the types of events, like interrupts, exceptions, etc. So this is an important point. So what I'm going to do now is I'm going to analyze an interesting scenario that we had in production, because we run in Oracle Ravello a lot of nested scenarios. And using this scenario, I will be able to teach you about another important mechanism. So we had a case that when layer 1 hosts are basically running layer 2 guests, sometimes about 5 until 10% of them is going to get stuck. And when we examined these hosts, what we saw is that all the layer 1 CPUs besides one are basically attempting to grab the MMU lock. But one layer 1 CPU is basically holding this MMU lock, and it is waiting for something else. And this something else is basically an API that he has sent to some target CPU, but for some reason is never accepted. So the next thing that we did is we basically reproduced this bug on a debug environment, and we traced what KVM at layer 0 sees. So you don't need to understand all the bits. I will just go with the translation. But the idea is that the first event that we saw is that we saw an exit from layer 2 to layer 0 on the attempt to deliver an interrupt D2. So like we said before, on this case, what KVM is going to do is to queue this D2 interrupt in an injected state, and also signify the KVM rec event. Now, before the KVM rec event handler has run, the next event that we see in the log is that also we got an API from another layer 1 CPU that resulted in queuing another pending interrupt waiting for layer 1. So now when the KVM rec event handler is going to be run before resuming the layer 2 guest, what will happen is that it will have both events queued. One is in an injected state and one in a pending state. Now what we see next on the log is that the next thing that happens is that the KVM rec event decided to take only the queued injected event and write it to the active VMCS, which is VMCS 02, and then resume layer 2 guest, which basically results in the reinjection of the interrupt. And the next event that we see is an exit from layer 2 to layer 0 on an EPT violation, this time not during attempt to deliver an event. And then we just resume layer 1. But something interesting we see here is that the KVM rec event is not signaled at this point. And therefore, layer 1 has never received its pending API, even though we have a pending interrupt in the local API, because no one is looking on this queued interrupt. So when we try to analyze and think about why exactly this happens, we understand, first of all, that the KVM rec event is not signaled at this point, and therefore the pending interrupt is not evaluated. But we may ask ourselves, at some point of time, we were at this scenario, that we have these two queued events. And what KVM decided to do is to take the queued injected event and re-inject it. But maybe we could have taken another decision. Maybe we could have taken a decision to take this pending interrupt and evaluate it and decide, because we have a pending interrupt, to exit from layer 2 to layer 1 on an external interrupt. But if we will do such a thing, we will need to also take this queued injected event and write it into VMCS 1.2. And this will cause the layer 1 guest to think that it got an exit on external interrupt during the attempt to deliver an interrupt. And this is a scenario that can never happen on a real CPU, because only a very specific exit can interrupt the delivery of an event. And external interrupt is not one of them. So we cannot take this decision, and KVM rec event did take the right decision. But if we try to think a little bit more on what we really wanted, we wanted that the event, which is in the injected state, to really be re-injected into the layer 2 guest, but immediately after the CPU finishes this injection, to exit back to layer 0 to reevaluate what should be done with the layer 1 pending event. So the way that this is implemented on how to fix this issue is basically leverage a mechanism called the immediate exit. And the idea is that sometimes we have a queued event that should result in an exit from layer 2 to layer 1. But because of some reason, we cannot actually exit right now from layer 2 to layer 1. Like in the case, we have a queued injected event for layer 2. So in this case, we can request an immediate exit. And the idea is that before resuming the layer 2 guest with the injected interrupt, what we can do, we can set KVM rec event, and then also disable the interrupt at the host, and issue a self API. And because the interrupts are right now disabled, this API is not delivered. and then we resume the layer 2 guest. Now, when the CPU will actually resume the layer 2 guest, because it has in its active VMCS an injected event, this will be injected into the layer 2 guest. And immediately after the CPU sees that immediately after the CPU injected the event to the layer 2 guest, it will see that it has a self-IPI waiting for the host. And therefore, it will immediately exit back to the host. And the host, because it has a KVM rec event now signaled, it will also evaluate what should be done with the layer 1 pending event, and therefore decide in this example to take the pending interrupt and exit from layer 2 to layer 1, as it should. So this was actually the fix. The commit title, I think, specified this very well, which says that the fix was basically to require an immediate exit when an event is reinjected to layer 2, and we have a layer 1 event pending. So this basically sums up a high-level overview of how nVMX event injection mechanism works. So what I will do now with the few minutes that I have left is basically go in a very, very high level on how the past year work that happens on nVMX. So I won't deep dive into everything, but as I said, we had a lot of fixes on the nVMX event injection. Most of them was actually very similar to the issue that you just saw. It's basically missing opportunities to reevaluate what should be done with layer 1 pending event. But we also, as a community, fix a lot of stuff, like supporting SMIs that are received in guest mode, and also better handle the case that layer 1 don't intercept external interrupts. And one of the, now it's written as a to-do, but this was recently fixed by Jim Matson. One of the big open issues that we had is that basically the user space APIs that are used to query the queued virtual CPU events and to set the queued virtual CPU events didn't know how to separate between whether an event is in a pending state or injected state. And this basically means that these APIs were broken for nVMX workloads. And it breaks things, for example, like nVMX live migration. Moving on to the next mechanism, we also had a bunch of fixes in nested APIC-V, mostly race conditions and also a bug that led to EOI exit map corruption. So this is very technical, but the nice thing about it is that after we have fixed them, we are now able to run ESXi as a hypervisor, layer 1 hypervisor on top of KVM with APIC-V enabled. And this wasn't possible before. You will encounter a bunch of weird states like ESXi losing network connectivity. And I don't have time to talk about the other to-do. Other things that are also interesting that we made a lot of improvements to nested MMU. Basically, nested VPID was completely broken. We invalidated sometimes the wrong TLB mappings. And we also optimized by removing a lot of TLB flushes. And because of Jim Matson last year KVM forum presentation, there was also a bunch of optimization to the layer 1 to layer 2 VM entry path. And we had a bunch of issues of exposing the wrong VMX features to the guest. This is mostly because it's very confusing because it's affected by multiple factors, as you see here. So failing to consider one of them causes you to the layer 1 hypervisor to basically fail. And this was all improvement to existing mechanism. Also, 2 new mechanisms that we have been implemented in the past year. One of them was pushed very hard by Google, which is basically nVMX migration support. The idea was that if we will be able to set the VMX features exposed to the guest from user space, and also be able to query and set the internal state used by KVM to run layer 2 guest, we will be able to migrate nVMX workloads that run nested hypervisors. Unfortunately, we still don't have the patches for using these capabilities in QEMU because Google don't use it. So I have submitted a patch series to do that. And the last new mechanism that I want to talk about is that we also, Jim Matson from Google implemented a mechanism called VMCS Shadowing Virtualization, which I have then further modified for upstream. And the idea is to support our really special use case of nVMX, which is triple virtualization, where the layer 2 guest is also a hypervisor that runs layer 3 guests. And the reason that this is complex is because if layer 1 don't have a VMCS shadowing feature, then it means that all the layer 2 VM reads and VM writes are going to trap to the layer 0 hypervisor. And also, these exits need to be reflected to the layer 1 hypervisor. So basically, the idea is to expose VMCS shadowing to layer 1. And therefore, layer 2 VM reads and VM writes don't need to even exit. But unfortunately, even this is already merged mostly, but it still doesn't provide for our production workload that actually needs it, good enough performance, and I don't have time to deep dive into the details, but I have put the details in the appendix slides. And there's still a bunch of open optimization opportunities that can be done to the series that I have submitted, but I don't have time to deep dive into that as well. So the other thing that I wanted to say is that all these recent improvements have gone to a really big milestone from my perspective, is that now Palo has created a commit that basically enables nested virtualization on nVMX by default from since kernel 4.20, which is really nice, a very big milestone. And I also promised to tell you about some personal opinions about the future directions of nVMX. So I think that the semantics of nVMX was horrible like 2 years ago, but now it's stabilized very well. And I think that now it's the time to improve the performance of nested workloads. And I think that Microsoft have proven that their PV interface for nested is getting really good performance. And the next logical step is to say, OK, let's have a similar PV interface also for KVM. And the reason that I don't say just let's use the eVMCS all the time is because the ones that are familiar with the eVMCS details knows that this is very tightly coupled to the PV interface of Hyper-V. And we don't really want to just expose all the time Hyper-V PV interface. But this also leads me to the thinking that if we will go with the approach of implementing a PV interface for KVM for nested, we'll eventually reach a scenario that every hypervisor implements its own PV interface of nested. Because we can mix and match all these different hypervisors between layer 0 and layer 1, basically we will reach with a very, very complex code, which I think it's a horrible future to imagine. So maybe we should draft a PV interface for nested, which will be cross-hypervisor, which I think can be very similar to eVMCS. We just need to modify it a bit so it will be more generic. Like the address should not be specified in a assist page of Hyper-V, for example. So to conclude, basically, nVMX has gone with a lot of enhancements over the past year. I couldn't talk about everything in only a half an hour, I'm sorry. But I have put, because I want to encourage other people to join the effort of improving nVMX, I've put a really, really, really big, like 5 lectures presentation in the appendix that you can all read to learn about this mechanism much more. And one more thing I wanted to say before finishing is that I believe that the KVM unit tests we have today for the VMX are very insufficient because they mostly test the edge cases and regression tests. And we don't have even basic functionalities tests for all the VMX features. For example, we don't have even a single unit test for virtual interrupt delivery. We don't have a single unit test for posted interrupts, etc. And I think someone needs to basically go over the entire VMX spec and just implement a basic functionalities test for each VMX feature. And like I said, we have a couple of big challenges ahead of improving triple virtualization performance and maybe drafting a cross-hypervisor PV interface for nested. So that's all I have to say. Probably no time for questions, I assume. There are? Wow, that's amazing. OK, so.
What did you mean by triple virtualization?
So basically, because I have a lot of appendix slides, I can just show you. But the idea is that in Oracle Ravello, we have a special scenario that we run nested workloads on top of a Google public cloud instance. So you can reach a scenario that layer 0 is the public cloud hypervisor. Layer 1 is another hypervisor, which is proprietary to us. And then we run a guest that is also a hypervisor, like ESXi, that runs VMs. So this is what I define as triple virtualization. And in this case, the layer 2, what is unique here is that the layer 2 guest is also a hypervisor. And therefore, it's going to execute things like VM reads, VM writes, VM pointer load, and things like that. Okay. Anything else?
Well, I'll just ask you, so do you view what you're looking at for the proposed PV interface would that help the scenario? Would an L3, would an L2 VM read, VM write be able to use that new PV interface instead to speed that up?
So yes, if we will have a good PV interface for nested similar to EVMCS, it will help the performance of this triple workload. Actually, one of the things that I try to do is to take the work that was presented in the previous lecture of EVMCS and put KVM as both being able to expose EVMCS and KVM utilizing EVMCS on top of each other. This actually led me to find a couple of bugs in that patch series, but it does improve performance a lot. So I agree that drafting a PV nested interface can maybe eliminate the problems with this triple virtualization. But there are a couple of more overheads.
So would you consider the triple virtualization scenario at least functionally stable at this stage already, just not optimal, or is there also some corner cases remaining?
So it is functional, it's not optimal.
That's good.
Okay.